Today is Friday, day 418 of data science. It is also September 9th, 2022. And today, basically, the idea is transforming nonlinear data to be linear in hopes of using that least squared regression line to be able to predict the weight of fishes. So I wouldn't even read this passage, though that's the goal, just be able to predict the weight of fishes, and the way to do that is by using a linear regression algorithm. And in order to use a linear regression algorithm, you need a least squared, what do you call it, LSRL, a least squared regression line, right? So a line of best fit. And that line of best fit is the one that has the less total distance, the total squared distance from the actual line, which I'll show or visualize in a second. So I already have the data frame. Um, Created here. I just imported pandas as PD, which is a data analytical library and can be used to create data frames. And so basically what I did, I took these two tables of data and just put it here in Python with pandas. And so yeah, so I did PD data frame, which is a function from pandas, and then I just put in a dictionary. I passed in the values of the columns, and yeah, I did that. And then I did df.head, which prints out the first two um, rows of the data frame. So I have length and weight. If I kind of remove this and just do df, I'll be able to actually see all of the values here. So you can see that happening. All right, but I'm just going to print out the first two to keep things clean. So I'm going to first visualize this data set. So to visualize, I'm going to import Seaborn, which is a data visualization library, or just normal visualization library. And then I'm going to do sns.scatterplot. So I'll use Seaborn scatterplot and plot in the length and the width, the weight, not the length and the width, the length and the weight of the fishes. And so I'll target the data frame, right, which is df, and then I'll put in the length. And then the second value I want to plot is the weight. And so you can think of it as just plotting x and y. These are your two variables. So now if I plot that, or run that actually, I'll be able to see the plot, and I can see the data plotted or scattered, and I can clearly see that it's not linear, which is a problem. And as I said, I already knew it was not linear. That's the whole problem here to solve, to transform this data so it could be linear, right? Because if I actually do SNS dot, I think it's a reg plot, I'll be able to see the least squared regression line, um, and I'll do a comparison like before and after. But if I run this, let's run this. You can see the line, and then if I believe there's a resid plot also. I don't even know, is it the resid? Let's see, let me search it up real quick. sns.resid. Oh, it's resid plot. Okay, yeah. So resid plot, run that. All right, so here's kind of the idea behind it. This is the residual. So the residual is the actual minus the predicted. So with your line, like with your data points, those are your actual values. And the least squared regression line is a line that it's like a line of best fit. It tries to fit in all of the values so that you can use that line to predict future values. And so right now, this is the least squared regression line that we have at the moment. But as you can see with that line, you can clearly see that there's a pattern in the residual plot, and you see that there's a lot of distance, around um, the line of zero. So you want the difference, right, from the actual value and the predicted value to be as small as possible, because again, you want them to be very close to each other, right? Like the difference or the values, because it means that you're doing a good job at predicting. If your how do I say this? If your predicted value is far from the actual value, then obviously you didn't do a good job at predicting, right? Because your result was different than the actual. And so this graph shows that you see the residual, so the difference between the actual and predicted, and you can see they're not really centered around zero, and you want your residuals to be centered around zero, because that means that there's a little difference between the actual value, like the real weight, and the predicted weight. And then you can see that here also in the residual line, because you can see that there is like a lot of differences here, and it's not really fitting to that line. It's not the line of best fit. So in order to find the line of best fit, you would have to linearize the data. And the way to do that is by two ways. You can figure out if it's an exponential model or a power model. And if you don't know from the get-go if it's exponential or power model, you can just perform the two ways to make exponential linear and power linear and see which one is the best fit. So I'll start by doing exponential. So if this was an exponential data set, then what I would do is I would just take the log of y. Oh, in that case, that would be the log of the weight, right? So I guess I'll take the data frame and I'll create, let's see, log of the weight and set that equal to np.log data frame weight over here. And then np comes from the numpy library, which I actually have to import. What did I just do? Okay, so import numpy as np. And so now if I do that and I do df, I'll actually be able to see the log of the weight. And so if I were to plot the exponential model, let me do df.head so I could actually not see that much. Then that would look like this. So sns.scatterplot, and then I would plot in my x values would be the length, and then my y value would actually end up being the log of the weight. So just think of it as x and y, just plotting x and y. Instead, we're plotting the length and weight, but in this case, it's the log of weight because it's the exponential model. What did we do today? Let's see. df log of weight, is that no? Oh, it's capital L. Let me copy this real quick, paste that in here. All right, so let me run that. Beautiful. And now we can clearly see that it is still not linear. So we can definitely say that this is not, this wasn't an exponential problem. So the last thing would be to do is to check for the power. But really quickly, I just wanted, actually, yeah, never mind. Well, I'll do the power. So the power model is just doing df. Let's do df. It's actually taking the logs of both. So I already took the log of y. I already have that as a value. So I'll just take the log of the length at this point and then set that equal. Basically, I'm creating a new column, right? And I'm setting it equal to np.log of df. And then let's do length, right? And then run that. And then if I run the data frame, I'm able to see that now as well. And so now I can just do, again, let me do df dot head and then 2, specify how many rows I want, so 2. And so now to plot the power model, I'll do sns.scatterplot and then do df log of the length because that's my x variable. And then for the second value that I want to plot would be the data frame log of the weight, which would be, did I say lowercase w or capital W? Oh, lowercase. Okay, so that would be like my y. What now? Did I spell it wrong? Capital L? So weird. Okay, and voila, you see that the data is linear. So obviously this was a power equation. So what am I saying? I can't even speak today. So let me reiterate that. You can clearly tell that this is a linearized data now, right? So that means that this ended up being a power model, and we just had to take the log of both the x and the y, so in this case the length and the weight. And now because we have linearized data, if I go ahead and plot let's do sns dot reg plot, which is going to show me the least squared regression line now. And if I were to plot let's take in these same values here, just paste that in there. run that, I'll be able to see the regression line. And now the regression line, you can obviously see that it's literally following the actual data points. And it's so much better because now when I use this line to predict my, my weights, the weights of fishes, it's going to actually give me really, really, really accurate results because the line is following really closely to the data points. And then to even have further evidence of that, I can do SNS dot resid plot, right? Again, and I'll be able to see the differences, right? You can clearly see that there is no pattern. So that's one thing you look for in a residual plot. And number two, the data points are mostly centered around zero. And you can see the ones at the right are mostly centered around zero. And that's really good because that means that the difference between, again, your actual value, the actual weight of a fish, and the predicted weight of the fish is very, very small. And that's what you want. You don't want there to be like a big difference between the actual weight of a fish and the predicted weight of the fish that you got from using your algorithm. So now this data is perfect to predict weight. So now I can predict the weight. So let's just make something up. Let's say I want to if I have a fish of length of, I don't know, let's do 2 point, I don't know, 43 maybe. So I can ask the question, what is the weight, or I guess what is the predicted weight of a fish whose length, yeah, let's whose length is what did I say again? 2.43. What were the units? Let me scroll up. In centimeters, and then the weight is grams. So I probably should have added that. Centimeters, question mark. So what is the weight in grams of a fish whose length is 2.43 centimeters? And so what I can do is um, just plug in the values here. So my actual equation, well, you might ask, how do I get the equation, right? So there's this thing called SNS, actually, from scipy dot stats import linregress. Let me run that. So now I can do, well, let me import scipy as well. So import scipy as CS instead. And I think if I just do that, I don't need, actually, let me do both. So I can do SC, so the scipy, and then stats.linregress. And then I think because of that, I don't need this because I already targeted the stats. And then here I can just put in the values that I want. So I don't want to put in the original data values like DF length and DF weight. I want to put the transformed data, and that's these two over here, the log of the length and the log of the weight. So if it just lets me copy this, which is actually not letting me copy it, so I guess I'll just write it here. So the first value would be DF, and that would be the log of the length, right? And then the second thing that I would want to apply is the data frames log weight, and then run that, and that's going to return to me the equation. So it's going to return to me slope. Well, actually, it's going to return to me the terms, and I have to actually make up the equation. So it's going to return to me the slope and the intercept, which is really all of that I need to make the equation. So you just have to know the format. So the format for this would be predicted y, and then you would do a plus bx, where a is your y-intercept and b is your slope. And in this case, my predicted y is equal to the predicted weight of the fish, and the x would be the length of the fish. So now I can just make up my equation. So now that I know that what's what, my predicted y, so I'm going to call it y hat, is equal to the y-intercept, which is this. So I'm going to copy this and paste that into here, and then plus, and then put in my slope over here, times x, and that is literally my equation. Now in context, I would just kind of copy this and paste that again and call it, predicted weight of the fish, and then this one would be the length of the fish. And so now I'm going to copy this and just make it into code, right? And then the only thing I would change is put a times sign in here. So I could do times the length of the fish. And so I'll set up my variables. So the length that I want, again, is equal to what? What did I say? 22.43. So 2.43. So now what it's going to do is going to return to me the predicted weight given the y-intercept and the slope and the length that I told it to. So it's answering my question. I'm just going to make sure that it actually returns that um, and prints that out. So if I run that, I'll be able to see the, what do you call it? The predicted weight of the fish. So this is what um, the fish, this just answers my question. So, what is the predicted weight in grams of a fish whose length is 2.43 centimeters? Well, it's going to be 3.036 or 0.366. That's it, so, grams, right? So I guess if I want to round that, I could. So let me do round to the 4 decimal places. And then maybe if I want to print that, I could do print. And then actually, hold up, maybe I could do answer, set that equal to that, and then I can print answer as a string, and then I could say plus grams with a space. All right, so that's my little thing here. And yeah, that's literally it. And it's pretty cool, you could just predict weight of a fish, I guess, knowing the length. And if I want to know what the length of, or what the weight or the predicted weight of a fish is, whose length is, I don't know, 1 centimeter, then all I have to do is change the length value to one and it's gonna give me that. Although, sometimes you have to make sure that these answers make sense. Like a fish cannot weigh negative 1.3, obviously. So then obviously this is not, relevant. So you would just, consider relevant things. So a fish whose length is 5 centimeters would obviously have a predicted weight of 10.8736 grams and whatnot. But again, I'm going to do 2.34 and leave it as that. And that's pretty much it for today. That's kind of the idea. Yeah. I'm going to go now. Bye.